Welcome to this course of Developmental Artificial Intelligence. This is something quite new. You don't hear so much about artificial developmental intelligence. So let me introduce myself. I am Olivier Georgeon. Here is my email on my website, and these slides can be found on my website. So, introduction to developmental artificial intelligence. I illustrated this with this picture of this strange animal. It is an archaic animal which accounts for evolution of species. So it illustrates the fact that we will be interested by basic intelligence principles, original principles in the phylogenetic evolution, and also in the ontogenetic evolution, that is, along the individual evolution of each individual. So we try to capture those two ideas. So how a newborn individual can, how can its intelligence develop from scratch? We try to capture these two ideas by going progressively towards more sophisticated intelligence. So this is an old dream of artificial intelligence. I can quote Alan Turing, who is considered as one of the founding fathers of computer science. And already in the 1950s, he wrote this. I let you read. Basically, instead of programming the intelligence of an adult, we could try to program the intelligence of a child. We could hope that those basic principles would be relatively simple. So just by programming basic principles of the child's intelligence, we could trigger an autonomous form of intelligence that would grow by itself. So if we find those basic principles, the problem will become a problem of education rather than a problem of programming. So this is an old dream of artificial intelligence, but it never came through. Already at this time, they anticipated that this problem would be solved in the year 2000, but it was not. And not only it is not solved, but we have very little ideas of how to manage to solve it. But we are working on it. So I'm going to present how we can get a grip on this problem, what we managed to do. Especially I'm going to show what we managed to do here in the University of Lyon. I'm working on a research project on developmental artificial intelligence. So this is something quite specific, and I hope you will like it. So you can ask a first question. Do you think it is even possible? Because of course you cannot deny the fact that it relates to consciousness. If you want to design a system that can evolve by itself, then it means that it has to give meanings to its experience. So it raises philosophical questions. Can we even imagine that it is possible to design a conscious artificial system? And here we don't have an official scientific response. The scientific community diverges on this question, and as a teacher I cannot bring you the response of the scientific community because the scientific community diverges. So everyone can have its own opinion. So we can do a little survey here. I'm curious to know who of you believe that it would be possible to create an artificial consciousness. And I'm not judging because I don't have the answer. So there are 8 students who think it is possible. So there are 5 who think that it's not possible out of 18 students. So who doesn't know? Oh, so some don't even position themselves by saying they don't know. So I'm not going to answer this question. I'm only going to present how we can get a grip on this problem and how we can formulate and attack this problem. So who wants to give arguments against? So it's not possible to program consciousness. But why? So yes, there is a lot of chemistry in the brain, and chemistry would not be mere computation, so it will not be possible to replicate all the chemistry in the brain. We not have the sufficient technology to address the complexity. So yes, there are 10 power 14 neurons in the brain, so we will never manage to model such a complexity. Okay, so maybe the most basic argument is that we would need a soul. There is something non-material in the mind, which is not material, and so we could not program it because we would not access to this immaterial entity that we need, a soul. So it's a spiritual vision of consciousness. There is another argument that you may have heard, the causal openness of physical reality. So it's linked to quantum theory, considering that we cannot predict the result of a quantum experiment. The current theory believes that there is a part of randomness in the result of a quantum experiment. We could imagine that there is a cause that is outside the physical world. So you can hear those theories that suggest that there is a cause outside the physical world that conditions the quantum indeterminations, on which could provide the origin of consciousness. And of course, there is those theories that you mentioned. It could be theoretically possible, but so there is no the need for a soul or no need for another universe. But it's only a problem of complexity. So it's only a problem of organization of matter, but it will be so complex that we will never manage to solve it. And there are many other arguments against, such as we don't see how we could program emotions, self-motivation, and so on. Because, of course, being conscious is about feeling something, and we don't see how a computer could feel anything. So the yes, it's the idea that consciousness can arise from matter. So it's a quite old idea. In fact, it is present. It has been present from the Enlightenment. In France, we have this guy, Julien Onfray de la Métrie, who lived between 1709 and 1751, who suggested that matter can think. It's just the idea that we are only matter, our brain is only arrangement of matter, only this can produce thinking and consciousness. And much more recently, there is the idea that to understand consciousness as a computational process. So if you want to learn more about that, there are the papers from David Chalmers, who gathers all these arguments and argues that it is possible because consciousness is only computation in the broad sense, in the sense that neurons implement a computation. So consciousness is only computation, and of course it will be independent of the support. So there is no reason why we could not implement this computation in silicium, because if this computation can work in vivo, there is no reason it cannot be implemented in other support. Because if it's just a computation, it will be independent of the support. Okay, so the outline of this lesson, I will show demos of developmental learning agents, and it's primitive work, but you will tell me what you think about it. And then I will present theoretical basis for this problem. So how do you lay the problem? And I will reach the conclusion that one of the key concepts is the concept of self-programming. How do you do a system that can program itself? So there are theoretical reasons, but it's quite obvious when you think of it. So if you think of current robots, they can only execute programs that we hard-coded. But what we would want is that if we put the same program in two robots, then depending on their individual experience, we would like them to develop individual behaviors. So self-programming means that the data that is learned is not only parameters or weights or values, but it is executable data. So how to design a system that can acquire executable data? So it raises many questions. So of course, a system that can program itself will not program itself to become Microsoft Office, so we don't know why it would do so. So it raises the question, what will be its own motivation to program itself in a way or another? In which language would it program itself? It won't program itself in Java, probably, nor any language that we are used to. Which execution engine would be able to execute this program? So here a student asks if it would require an interpreted language rather than a compiled language. So it's totally open. It's a good question. Indeed, not only self-programming is hard, but compiling itself is even harder. So it requires to assume that the interpreter pre-exists. Okay, that's interesting ideas. So all the course will try to answer these questions. Then the second part of this class will be an exercise about how to implement your own self-programming agent. So that will be really the basic of implementing a self-programming agent. So let me start with a little demonstration. So we think, if we imagine a baby that is just born and who tries to learn So it has muscles and it has a sensory system, but it has no knowledge of the world, so it makes random gestures. And when it makes gestures, it has some feedback. And I try to capture this idea with quite simple experimentation. So imagine the agent has those 6 possibilities of experiment, and it has no idea what they mean, but it can pick one, each one at random. And imagine that for each of them, it has one possible bit of result. So it tries this experiment, it gets this result, try this one, it gets this one, and so on. And the result does not reflect the state of the world. So in the same state of the world, one experiment may return 0 and another experiment may return 1. So it's not, the return is not an information about the state of the world, it's only a feedback on the experiment initiated by the agent. So we may imagine a system that will just babble. It's not reflecting, it has no strategy, it's just babbling. And it can observe regularities in this experience. So we'll think in terms of interactions. So if it does this and obtains 0 as a feedback, then it made this interaction I1, and if it's that and that, it obtains I2. If it does its experiment and receives this result, it has enacted interaction I3, and so on. And with I3, it has in fact no information because it returns always the same result, but this experiment may change something in the world. If it does that and receives 1, it's interaction I5 or I6, and so on. So we'll confront this agent to an environment that has regularities of interaction. So for example, if it enacts I8, that is do that and receive that, then in this context, if it do that again, it will probably receive again 1. So enact again I8. And then that might be more complex regularities, such as if I enact I7, then if I try to do this experiment, then it's more likely that I obtain result 0 than result 1, that is enact I1 than I2. And then there could be longer regularities. So if I did that, I could enact this whole sequence of interaction. And then if I enacted this longer whole sequence, then it's likely that I can subsequently enact this whole sequence. So we expect the system to discover those regularities, encode them and memorize them, and reuse them. So reuse them to do what? For 2 things. We will implement a system that will simply like to predict what will happen. So it will be happy if it managed to find a situation in which it can anticipate what it can do next. So it's as if it had the pleasure to master the interactions between its environments. So in fact, we implement a system that tends to discover regularities and exploit them. And when we look at this system, it will seem to us that it has some pleasure to control its interaction with the environment. And there will be a second form of motivation. Interaction will have values. So some interactions will be positive and some will be negative. And we'll implement a system that will try to enact positive interactions and avoid negative interactions. So this allows us to implement a motivation to, for example, to like eating. So we'll create the interaction to bite on something and swallow something and give it a positive value. So the system will try to enact this interaction. But of course, if there is nothing edible in the environment, it will try to bite, but it will fail. So its intended interaction will not be it's actually an acted interaction. So it will have to learn to place itself in situations in which it can enact positive interaction. So in this case, there is only one positive interaction, I1. So the system will like to enact I1. So we try to execute this experiment, but if it results in I2, it will be highly negative. So it would have to find regularities and put itself in situation in which, when it tries this experiment, it indeed results in I1. And then other interactions are slightly negatives, so it will have the possibility to use those other interactions to place itself in situations in which it can enlarge this positive interaction. So that's this example corresponds to the idea that you have about learning from scratch. If interactions had no value, then it would have no reason to learn, because everything would be equal for it. So, for example, bumping into obstacles hurts, and eating is enjoyable, so it has this kind of motivation, but it's not its only form of motivation. It has also this tendency to learn just for the pleasure to learn. And we found that if we don't implement those two kinds of motivation, it doesn't work. So we can imagine an experiment in which all the values are set to 0, and then it will only learn based on the pleasure to control its activity. It will be just learning for the pleasure of knowledge. So yes, it corresponds to this idea of being driven by the desire to learn, and at the same time being driven by innate preferences. Okay, so let me show you the experiment. So the agent ignores what these interactions means, but we look at it from the outside and we understand what they mean. So the agent is this triangle here, and there are empty cells on the walls, and this interaction means to try to move forward. So if there is an empty cell in front, it means it moves forward, and if there is a wall, it bumps into this wall. So we give a positive value for moving forward, meaning it likes moving forward, and a negative value for bumping into walls. But again, it has no idea what they mean, and it doesn't even know that it is in a space. Then those means he can turn to the left and to the right, and it will always succeed. And all of these 6 here correspond to touching, to feeling by touching. And there is touching to the left, touching to the right, and touching in front. But it has no idea of left and right and front. It has no idea of space. So the interaction touch doesn't change the environment. The agent doesn't move, but it returns an information about the state of the environment. But the agent ignores that it moves or doesn't move, and that it corresponds to a state of the environment. So this demo is online. You can find it on our website, and you can modify the values of interaction. So any value you would set here, it will learn to use the possibilities of interaction that it has to control its interaction and to get positive values. So at the beginning, it picks interaction randomly. It has no idea what they mean. So when it touches the wall or a cell, the cell flashes yellow. So you can see when it touches, and when it bumps into a cell, the cell flashes red. So it learns those regularities in time that I showed you in the previous slide. So of course, after a while, it realizes that when it touches in front and it's empty, then it can safely move forward. So it learns that it's a good idea to touch forward before trying to move, and not to move if it touches a wall. So it gradually gives a meaning to the interaction touch. So it's more than learning that it should not move forward when it touches in front, but it's engaging in active perception. And then it learns that if it touches a wall in front, then the best is to touch on the side. And then if it touches an empty cell to the side, it learns that it better turn toward that direction so it can move forward again. So here the student asks if it constructs a map of the environment. So no, it does not construct any map of the environment. It's only a sequential learning. So it learns episodes of interaction. It does not learn the entire sequence of turning around the loop. It learns mini sequences and find mini sequences that can be reused and exploited. Donc, mettons, il aura, au bout d'un moment, il aura repéré que quand il a fait cette séquence-là, celle-là serait possible. Et en plus, il regarde sa valeur. So after a while, it realized that after doing such, for example, 2-step or 3-step sequence, then it can subsequently enact again a 2 or 3-step sequence. So that is what allows it to go through negative interactions in order to reach even more positive interactions. So it can find that it is a good idea to enact negative interactions, such as touching, in order to put itself in a context in which it can enact positive interactions. So I will answer those questions in the following slides. So let me play it again, because it looks quite rudimentary, but that's something you probably never saw elsewhere, because it's more than simple stimulus-response adaptation. It's not only about learning that if I touch something, I should do that, but it's about engaging in active perception. So it doesn't know at the beginning which is perception and which is action, but it learns, it finds that certain interactions can be used as a perception of its environment, to characterize its environment. So it learns to actively perceive its environment. So it's the fact that it can learn sequences and characterize a sequential context that allows him to do that. So that's why we designed this environment as a little loop, because it amounts to a purely sequential problem. I will show you later other examples in a spatial environment, but so far it's only sequence learning. So it learns to circle the loop, but what interests us is not so much that it circles the loop. What interests us is that it learned to use touch interaction to perceive its environment and characterize its context. But as it learns longer and longer sequences, and after a while it learns sequences that allows it to make a full tour of the loop. So if you want to place this agent is an open environment, it won't manage with only sequences. Okay, so I'm going to show you another example with 2 agents. So it's the same experiment, But we have two agents. So it's the same experiment here. It's not flashing yellow or red, but there's those little squares here that represent touching and bumping. So the agent on the left here is trained in the little loop, and the agent on the right is not trained in this restricted environment. So what we see here is that this orange agent on the left, when it has been trained, we will open the loop and to show that what it has learned can be used in a more complex environment. Okay, so we open the loop. So we can see that it has learned that it should touch in front and touch to the left and to the right. So it has well understood that, so it can use that in a more complex environment. So in this experiment, it has no way to interact with those little flowers here and color blocked. It does not see the difference between flowers and empty cells, and it does not perceive the difference between color walls and regular walls.
Mais il a appris, disons qu'il a appris à percevoir au moins ce qu'il est capable de sentir par ces interactions, il a appris à les percevoir activement, à adapter son comportement. Et alors, en fait, là, ce que ça montre, ce truc-là, c'est que ça montre cet effet d'entraînement. Si vous
So this shows the effect of self-programming, because the two agents that have the same algorithm don't develop the same behavior. So if I play it again, and if you look at this blue agent now on the right, you will see that it will not learn exactly the same behavior, because we did not train it in a simple environment. So he did not find the same regularities. It only learns that it should touch before moving forward and not move forward if it touches the wall, but it does not learn this strategy to touch to the left and to the right. So it develops less efficient behaviors. So it tends to get stuck in loops, just like this, because it does not touch on each side when it faces a wall. So it has found a pattern that works, and it is stuck in this pattern, whereas the other agent that has developed more sophisticated behavior will not get stuck in such a pattern, because it will turn to the left and to the right. So it only finds a behavior that works, and they don't find the optimum behavior. They just find one possible solution to satisfy their tendencies. So what it shows that there is an individuation of each agent. We did not encode those specific behaviors, but depending on their own individual experience, they will develop different behaviors. And the other agent feels like a wall. So it does not know that there are other agents. It does not make the difference. Okay, so who thinks he could encode such thing like that quite easily? Well, not easily. Okay, so no, it's not that easy to generate those kinds of behaviors, and so I'm going to present a theoretical background to explain why it is important to study those things and how do we address this problem. So there is a whole theoretical field behind this. So there is philosophy of mind, as I mentioned earlier. There is epistemology, that is theory of knowledge. So of course we have to think about what does it mean to learn anything. There is developmental psychology, theories of how a newborn infant learns from scratch. There is biology or neurosciences. So philosophically, so that's the question, is it even possible? So as I said, for the last 300 years, philosophers has told us that matter can think, and it should be, they produce philosophical argument to support the idea that only a material system can generate cognition. And more recently, we have, as I mentioned, David Chalmers, who suggested that consciousness is only a matter of computation. So it's I should also mention Daniel Dennett with his book Consciousness Explained. In particular, it talks about some crucial questions, the question of free will and individual choice. So what will generate the impression that an agent has its own motivation? And there is a key concept here. It is that a process can be totally determinist, but nonetheless give rise to individual freedom and free will. So that's what I tried to illustrate with those two agents. So the learning mechanism of each agent is totally determinist. There is no random function. So if you run them twice, they will do exactly the same thing. Nonetheless, they are unpredictable in the sense that if there is a little difference in their individual experience, they will not develop the same. So the agent in the small loop that you showed earlier, if you run it twice, it will do exactly the same thing. And yes, I did not insist enough on that, but this is why we have those buttons on the bottom here that can make you choose the initial position. So if you run it a second time in the same initial position, it will do exactly the same thing. But if you begin with a different initial position, then it will learn different things. So sometimes it may learn that it may circle the loop in the other direction, for example. And sometimes it does not find optimum behavior, so it may stay on an edge of the loop and make a U-turn on each side of the loop, which is a little bit less optimum than circling the loop, but it's still good. And of course, you can change the values for interaction. So if you set a positive value for turning, then it will make a few tries, and then it will find that it can just spin around to get positive value. And if you give a positive value for bumping, it will stay in front of a wall and keep bumping. So that's the interesting part. It becomes quite intuitive. That means that with these cursors, we define the pleasure that it associates or the pain that it associates with each interaction. This is because behind that there is this algorithm that can learn regularities and organized behaviors depending on these values. Knowing that it can use slightly negative interactions, so it's not only adapting towards immediate higher value, but it can use, it can go through negative experience in order to reach more positive experience. So if we put everything negative, then it will find the less negative interactions. Knowing that it's not optimum, so it may not find the less negative one.
Donc philosophiquement, ce qui nous intéresse, c'est que
okay, so philosophically, the key ideas here are that cognition is a computation. That is, what does it mean, a computation? It means that there is a chain of cause and effects in the very broad sense. So we think of the brain as a dispositive, a causal system, complex, based on neurons and chemistry. So yes, there is chemistry, there is neurotransmitters and hormones that might modify this causality. So this causality is complex and smooth. But it's still a causality. That is, we don't see a reason why it could not, this causality could not be implemented in silicium. So also, as I said, this notion of determinism and free will is an important question. So we can have a system that is totally determinist, meaning that if we run it a second time, it will do exactly the same thing. But nonetheless, each individual may develop its own understanding of the world based on its own experience. So this effect of finding episodes and re-execute episodes is this effect of self-programming, and because it does that, it becomes different from other instances of agents that would have learned different episodes. And this is what gives us the feeling when we look at it from the outside that it begins to understand its environment. If there was not this individualization effect, then it would not look so smart.
Alors, comment on utilise aussi, il faut avoir un peu des bases d'épistémologie, c'est-à-dire des théories de la connaissance au sens large, c'est-à-dire
okay, so we need also some concepts from epistemology. The concept of ontology. I don't know if anybody had already introduced the concept of ontology to you. Unfortunately, no. So ontology comes from the Greek ontos, means being, and logos means discourse. So it's the discourse about everything that exists. So it comes from Aristotle. So Aristotle wrote a treatise of everything that existed in the world.
Donc comment peut-on connaître tout ce qui existe dans le monde? Donc, par exemple, si je vous dis,
so it is about how can we know everything that exists in the world. So for example, if I ask in this classroom what exists, what does exist, so you would say there are 18 persons, there are 20 tables, 40 chairs, but you can never really know all reality. So you can still say, yes, but there is also dust, there is also atoms that constitute tables, and so on. So you can break that down to some more fundamental constituents. So the question of how do we know what exists in the world is an open question. So you can have more information about the concept of ontology, but I wanted to introduce this concept because implementing a developmental agent will be about implementing an agent that will be autonomously able to learn what objects exist in the world. And the key idea here is that we don't want to design agents to which we give knowledge of the world a priori. So in the example I showed you, the agent ignores that there are objects such as walls in the world and empty cells in the world. It's up to it to learn the existence of these categories of entities that exist in the world. So you will learn more about ontology in the class of expert systems and reasoning engines.
Mécanisme de raisonnement, par exemple, on pourrait faire des agents, on dirait, bon, bah, s'ils sont face, ils auront une connaissance qui est que dans le monde il existe des objets comestibles.
So for example, in an expert system you can encode the idea that in the world there are edible objects and there are fruits, and fruits are kinds of edible objects, and there are some objects that are apples, and an apple is a kind of fruit, and a fruit is a kind of edible object. So if you see an apple, you can try to eat. So you can implement this kind of reasoning. So this is traditional symbolic artificial intelligence in which you encode an ontology of the world, in which you define all the categories of objects in the world that exist. So we don't want to do that because we don't want to tell the agent a priori what it will encounter in the world. We want to design agents that discover by their interaction, through their interactions, what exists in the world and understand the world through their own experience of interaction. And categorize the world depending on their own motivation, so depending on what matters to them. For example, if they have positive interactions and negative interactions, those objects that afford those interactions. And philosophically, we know that anyway, reality as such is unknowable. So if we wanted to design a robot that can interact with the real world, it would not be possible to encode all the objects that exist beforehand. So we could encode that if you see such a shape, it's a table, so you should behave like that. If you see this kind of shape, it's a chair, so you should behave like that. But there is an infinity of situations, and it will not be possible to encode all of them. So this is why we want to design robots that can learn to discover the world by themselves. And even ourselves, we don't know all the objects that exist in the world. So as we progress, for example, in physics, we know that objects are constituted of atoms, and atoms are made of smaller elements, and we'll never know the ultimate essence of reality. The only thing that we know is what we can interact with, either directly or indirectly. So the key idea here is to base all knowledge on interaction. So that the agent will construct its knowledge of the environment from its own experience of interaction. So we say that we implement systems without ontological assumption about the world. That is, without encoding in the system a list of all the objects that it will encounter. So we propose the notion of agnostic agent, meaning that the algorithms that I showed you, we can put them in any kind of environment, and they will always learn regularities of interaction to regardless of what these interactions mean. And we cannot even prove that the agent understood its world. We can only show that its behavior got well organized. So that doesn't mean that we don't do any assumption at all. We do assumption when we create our agent, but those are assumptions of possibilities of interaction. So we predefine the possibilities of interaction of the agent. So, for example, if we build a robot, we define its possibilities of interaction by choosing its motors and sensors. But we don't define what it will find through interaction. So it will have to experiment to construct its own knowledge of the world by itself. Okay, so another source of inspiration is developmental psychology, which addresses the question how can we learn from nothing? So there are many people who theorized about that. So especially there is Jean Piaget, 1896-1980. So we get closer to the modern era. So he theorized on how a baby that comes into the world can, from its own experience of interaction, begin to construct a knowledge of the world. So he proposed some concepts that can be useful to us. The concept of teleology, meaning that the baby just born was not born with a predefined objective. So, for example, you were probably not born with the objective of being a computer scientist. It's something that you constructed along the line. So this differs from most traditional artificial intelligence, in which people study systems that can reach a predefined goal. So in developmental AI, we don't want to do that because we don't want to formalize the problem beforehand, and we don't want to implement agents that solve a predefined problem, a problem that we defined from the outside. So in the example of the loop, it looked like a maze, but it's not a maze because there is no exit and there is no final point to reach. So here, of course, the student asks, if staying alive can be thought as an objective. So of course, we have to make the difference between a concrete objective and an abstract objective. So of course, you can think that your objective in life is to stay alive, and maybe it would be the source of all your motivation. So maybe the reason why you work and you study is to be able to eat when you are hungry and be warm when you are cold. So staying alive may be seen as an objective, but it's not this kind of objective that you can reach. So it's not a point to reach. So you cannot measure that. You cannot design an algorithm that will maximize the probability to stay alive. So in our algorithms, of course, the result will be that the agent will stay alive. So if we give a positive value for eating, the agent will tend to eat, and the result will be that it will stay alive. But it's not because it is aware that it would die otherwise. And what we want is that it construct its own objectives, its own problems, even though this motivation rests upon predefined drives. Another key idea is that we should not separate perception and action. So this does not only come from Piaget, but the whole psychology of perception explains us that perception is not just about interpreting data that comes into our face. So, for example, the eyes do not work as a camera. We have this impression that we receive this image from the world, but in fact, if you look, for example, at the image that forms in your retina, it's very blurred. It's only knit in the fovea area, and it's the fact that you scan the environment with the eyes that generates this idea that you get a clear image of the surrounding environment. So this idea of active perception and interaction with the environment is central. It is from this interaction that we construct a knowledge of our surrounding environment. And as Piaget said, a newborn baby at the limit has no reason to believe that there exists an external world surrounding it. But because there are regularities in its possibilities of interaction, so when it moves, and it moves again and bumps into a thing, and bumps again into a thing, it comes to the conclusion that there is something that exists that causes this experience. But we'll start with the notion of interaction, the notion of sensory motor scheme, as Piaget named it. So from that, it elaborated the whole constructivist epistemology, and there are other theoreticians such as Jean-Louis Lemoigne and Ernst von Glasersfeld that theorized on the fact that learning is not only about interpreting input data, but constructing knowledge through interaction. So, psychology of development identified developmental steps. So it is very approximative here. You have to be careful. It's all those mechanisms probably exist from much earlier. But what those milestones here mean is that at those different ages, you can reveal those learning mechanisms with experiments. So on the 4th month, you can, for example, make experiments such as you have a bag with a lot of white balls and a few red balls, and when you get a ball out of the bag, the baby is able to anticipate which color of the ball is the most likely to appear, and if it's a red ball, it will be surprised. Then on month 5, it can predict the movements of hands. So you can make experiments in which it will be able to bypass obstacles with his hands. So on month 6, you can make experiments in which it can recognize people by their face. On month 7, you can make experiments that evidence the fact that it has a notion of persistency of objects. So if you put an object in a box and you close the box, and when you open the box, if the object is not there anymore, the child is surprised. So this again shows that the baby has no presupposition about the persistency of objects. So it discovers that objects exist in the world. On month 8, you can do experiments such as if you put a ball on a table or a toy car, it can predict that the ball can go in any direction, but the toy car will move only in one direction. So it has a model of the dynamics of objects. And then from this green line here, it differentiates a little bit. It's not as simple as that, but it differentiates human babies from other babies. So from 9 months, human baby can use tools. It's not necessarily only humans, but it's indicative. And then from month 10, it can imitate gestures. Again, not only humans do that. And then on month 11, it walks, and 15, it walks alone. Okay, so the key ideas here is that to think in terms of interactions, sensory motor schemes, as proposed by Piaget, rather than separating perception and action. And it's focusing on an intermediary level of intelligence. So higher level than stimulus-response adaptation, but lower level than reasoning and language. So it's an intermediary level that we could name semantic cognition in reference to the construction of meaning. So what are the mechanisms needed so that we can say that an agent begins to understand its experience? So we focus on this intermediary level of intelligence because we know that it is a mandatory step if we want to move on towards higher level intelligence. Because currently, of course, we know how to implement automatic translation, automatic word processing, but it's kind of mechanical translation which is not based upon understanding. But if we want to have a higher level intelligence based on understanding, then we have to address this intermediary level called semantic cognition. Okay, I'm doing a little break here. Okay, so as I said, we also can take inspiration from biology, and especially we can draw an interesting notion from biology, which is why even should we learn? And the main reason, as we said, is to stay alive. And if we think of what it is to be a living system, it is basically a system that stays alive and constructs itself through its interaction with its environment. So the people who theorized on this introduced the concept of autopoiesis, which comes from the word auto means self and poiesis means creation, so a system that creates itself. So how to create a system that can construct itself by taking materials from the environment. So an artificial cognitive system will be similar. How can it construct itself through its interaction with the environment? With this idea that there is a coupling between the environment and the system which defines the possibility of interactions, and this coupling must evolve around time. So if this coupling is fixed, or if the possibilities of interactions are pre-programmed, then it is not really a living system. So what we expect is to design a system which will evolve its possibilities of interactions with the world. So the notion of structural coupling is how to define the coupling between the system and the environment. And the relational domain is the set of possibilities of interactions that exist between the system and the environment. So, for example, in the experiment that I showed you, the relational domain is the set of all possibilities of interactions. There were those 10 possibilities of interactions between the agent and the environment. So we will want to design systems with a greater set of possibilities of interactions, and additionally a possibility to acquire new interactions. So this set of possibilities of interaction will have to grow. There is also this important notion of homeostasis, which refers to the regulation of internal variables, such as temperature and chemical variables, and which provides a measure of the livability of the system. So, of course, we want to design a system that will stay alive, so regulate those variables. But of course, it's when you are dead, it's too late to learn what you should have done to stay alive. So there is a reflection here. How in fact, we have innate preferences that guarantee our survival as an individual and even as a species, but we don't enact those behaviors because we are aware that we have to, otherwise we would die. It's innate behavioral tendencies that evolved over evolution of species that makes us having these preferences of behaviors and innate behavioral proclivities. So how this motivation works? So of course it's connected to the idea that to the motivation of not to die, but how is it implemented so that we enact those behaviors that as a result will preserve our life. There is also this theory of enaction, which suggests that acting is central in the learning process, and voluntarily acting is crucial. So there are some experiments in which they use newborn kitten, and they tied a newborn kitten in a little carriage on the back on another one by peers. So the one could move freely, and the other one was tied to the first one and could not move freely. So they had the same experience because they saw the same thing, but the second kitten was totally passive. And the fact that it was passive made that it learned nothing. And when it was freed, we saw that it didn't learn anything about how to interact with the world. It was like blind. So those theories has been applied to artificial intelligence. There is this paper, Enactive Artificial Intelligence, that discuss how to implement these ideas in artificial system. And they argue that this idea of self-programming is crucial because two instances of agents will end up doing different choices because of their different experience. So constitutive autonomy is necessary for sense making. It is because a system will develop its own personality that when we look at it, we can say that it starts to make its own sense of its experience. And this can be achieved through self-programming, of which I gave a first example, basic example, in which the agent learned sequences of interaction and could re-execute those sequences of interaction. So last source of inspiration is neurosciences, of course. So what do neurosciences tell us? So they tell us first that there are multiple levels of analysis, going from each individual neuron. So we know that a single individual neuron learns. So the learning does not occur only in the connection between neurons, but even inside each single neuron. So depending on your experience, one single neuron can change its information processing function. So inside the neuron there is learning. Of course, there is learning in the connection between neurons, the synapses. Then neurons are organized as columns in the cortex. So in the cortex, neurons are organized in columns, and we can identify columns. And we could think that maybe to implement an artificial system, we would not have to model each individual neurons, but maybe we could. It would be enough to model columns. Then there is a higher level in which there are larger areas in the cortex, and you could think that maybe it's no use to model each column of neuron or each neuron, but what is interesting is to model each area of the brain. We can even be at a higher level with functional boxes like this. So maybe one day we'll manage to create an artificial consciousness, but we have no idea whether we'll be obliged to reproduce those lowest levels of processing, or could we do it at the intermediary levels. So maybe those at the beginning who answered that they thought that it would not be possible, maybe they thought that we would have to model each individual neurons, and because there are so many, we will never manage. And those who thought it would be possible, maybe they thought that we could solve this problem at an intermediary level that would be manageable. And what's interesting also is that there is both a lot of plasticity and a lot of pre-wiring. So if you look at, there is this animal called C. elegans. It's like a small worm of a few millimeters, and each individual always has 302 neurons. This is determined genetically. So each individual has a fixed number of cells, and they are organized the same, and they have the same numbers of neurons, and they are connected the same. So there are thousands of synapses, and this is the connectome of these animals. So we know which neuron is connected to which, but we are still unable to explain its behavior. So we know that each animal can learn, even though it has a fixed connectome, but it can learn from its individual experience. So there is some plasticity at some level, but it is based on inborn wiring of neurons. Concerning humans, we are also currently working on the human connectome. You can look at this website, the Human Connectome Project, and see those beautiful images. So they try to determine which area of the brain is connected to which. So here again there is plasticity, but there is a lot of inborn connections. The reason why we managed to do this collecton is that it's similar from one individual to the other. So if you will, what it tells us is that we cannot hope putting neurons in a bag and shake it and obtain a brain. You will have to design carefully the structure of the brain. There is a lot of innate that specify the organization of the brain. So a student asks that this is the connectome of a developed brain, but if we start from a single cell, maybe we can hope it can develop like that. So maybe, but we don't know how. So we'll have to know how we want it to develop, and then we'll have to think how we could encode that so that it develops this way. Well, it's an open question. Also, there is no rupture between the human brain and the other mammals' brain, for example. So here are the brains from a hare, a dog, a chimpanzee, and up to a whale, included the human brain. So the human brain is not the biggest. There are whales that have 9 kilo brains. So what it tells us is that there is nothing really specific in the human brain that gives us the ability to develop language and resonate. So probably other animals are able to proto-language and rudimentary forms of communication, which are not fundamentally different from human language. So it's a matter of degree and level of skills. There is no qualitative rupture. So this suggests that we should already focus on the level of intelligence of a cat or a dog, for example, and we are ages from reaching this level, and we should focus on this level before even addressing the problem of human intelligence.
c'est pas qu'une question d'acquis, c'est-à-dire si vous élevez votre...
So there is no break in the evolution, but there is still innate differences. So if you raise your dog as a human child, it will never become a human, of course. So there are inborn structures. And overall, we can see the brain as a device to organize behaviors in time and space. Because obviously the animals are in time and space, and their brain helps them organize their behavior in time and space. And if we see it like that, this suggests that we should begin with a concrete problem of organizing behavior in time and space before addressing the problem of navigating in abstract ideas. So maybe our ability to navigate in abstract ideas rests upon basic mechanisms that allows us to navigate in space and time. So there is this hypothesis that suggests that those mechanisms that allows us to organize our behaviors for going from point A to point B will give rise to higher level behaviors or mental simulation to navigate from abstract ID A to abstract ID B. So the conclusion on the neuroscience is, so renounce the hope that it will be simple. So it will probably require decades of research to solve this problem. So we could address the problem at the multiple levels, but maybe we should not model each individual neurons, but address the problem at an intermediary level. And if it does not answer our questions, we could go down one level. So biology can be source of inspiration. So by looking at how the brain of animals is organized, we could maybe draw some inspiration. And I will talk more about that next week. And the importance of the capacity to perform internal simulation of courses of behavior. So if we have a system that can learn sequences of interactions, then we can design systems that can simulate those sequences of interaction in order to assess whether they will work or not work. And maybe this is the basis of reflection. So it's not an abstract conceptual reflection, but it's the basic capacity to reflect upon experience. So we reach the conclusion of today's presentation. So the key ideas that are takeaway ideas. So we'll try to implement a system that learn, meaning discover, organize, and exploit regularities of interactions in space and time. So we assume that those regularities exist in the coupling between the system and its environment, and we design a system that discovers and exploits those regularities. And we do that without encoding presupposed ontological knowledge about the environment. That is, without encoding our knowledge of the environment in the system. We want the system to construct its own knowledge of the environment. And by allowing some kind of constitutive autonomy, that is permitting some self-programming. So this is the teaser for next week. So look at those two animals here that looks like gray sharks. So they explore their environment. So they can see silent objects in their environment, and they discover that, so here they play together, and then they discover that fish can be eaten. So what it shows is that at least it allows a designing agent that whose behavior looks quite natural. So with this self-programming mechanism, we managed to do system that looks as if they had their own motivation much better than if we were programming all their behavior beforehand. So could this system develop a form of management of the fish resource? So we could imagine everything, but we are not yet there. Okay, so we are going to do exercises. So here is what we are going to do. So we are going to begin very simply. So we have an agent in an environment. On each cycle, it has one bit of choice. You can choose experience 1 or experience 2. And it has a result from this experience. Again, one bit, R1 or R2. So we don't know what it means, but it doesn't matter. So I can press this button or press this button, and I have this result. So I have 4 possible interactions. So I do E1, I receive R1. I do E1, I receive R2. I do E1, I do E2, I receive R1. I do E2, I receive R2. So E cross R is the interactional domain, all the 4 possibilities of interactions. So we'll create 2 environments, environment 1 and environment 2. So environment 1, when the agent says I want to do E1, then the environment returns R1. And when the agent says I do E2, the environment says returns R2. So environment interactions I1, 2 and I2, 1 that do not exist. And then we'll have environment 2, in which when the agent does E1, it returns R2, and if the agent does E2, it returns R1. So here the interactions I11 and I22 do not exist. So we'll put our agent in either of these environments, and we'll want to see that it adapts. And we'll have different motivational systems. So we can, so in the first case, we'll have interaction I11 and I12 that has a positive value. So we'll try different, so we'll implement an agent that whatever its positive interactions and whatever its environment, it will learn to enact positive interactions and avoid negative interactions. So we'll play with different values. And the agent doesn't know in which environment it will be put and which values will have interactions, but it will learn to enact positive interactions in this simple environment. So this agent will not have to learn much because those environments are quite simple.
répondre à cette question tout de suite. Dans le dernier point là,
So last point here.
comment
So how do we see that it learns? So we will analyze its behavior. So we want to see in its behavior that at the beginning it is experimenting, and depending on these experiments, it will learn what to do. So the question of behavioral analysis is crucial. So I'm not only asking you to program those agents, but also to return a report in which you analyze the agent's behavior. So it will be quite simple because those environments are very simple. So what we don't want to do is to encode knowledge, it's to encode our knowledge in the environment. So we don't want to do this thing. We don't want to test. So if the environment is environment 1 and motivation is motivation 1, I then choose E1, and it's environment 2 and motivation 2, then do E1. It works also. But we don't want to do that. Why? Because if we do that, that means that we implement our knowledge of the environment in the agent. Instead, we want an agent that experiments by itself the environment. So we'll do like this. So here I give you the structure of the program. I'm just asking you to code it on the basis of this structure. So you have a main method that will instantiate the agent and instantiate the environment. So by commenting this line, we could change on instantiate environment 1 and or environment 2. I'm not asking for a complex interface here. We define the different possible experiences available to the agent. We'll instantiate E1 and E2 and the results R1 and R2. And we'll instantiate the interactions. So an interaction will be an experience, a result, and a value. So we will make different tries with different values. So again, no complex interface. We can just change the values in the code. And we'll see that the agent adapts depending on the different values. And we'll make this infinite loop. So the agent will choose an experience, either E1 or E2, depending on the previous result. So at the beginning there is nothing. And the environment returns a result based on this experience. And then we display on the console the experience, the result, and the value. So the result will be what is displayed on the console, which constitute the trace of behavior. So at the beginning, we'll see that it will get negative values, so it will change and adopt experiences that returns positive value. So we'll have an agent class that with a method that returns the experience that the agent chooses. So it will have to memorize the results that it received previously. We'll have a class environment with two subclasses, F1 and F2, with a method give result from the experience chosen by the agent. So again, it will be quite simple. A class experience, a class result, and a class interaction that we can create from an experience, a result, and a value. And then we'll have a method get value, so we can get the value of an interaction. Okay, that's it.